the reckoning of time, but also the concept of time itself, were very firmly entangled with astronomy, more specifically with celestial motions and with the periods of cyclical recurrence that arise from these motions. The most straightforward example, of course, is the 24-hour day, which is based on the diurnal revolutions of the heavens. That's essentially the shortest of all these celestial cycles. The longest celestial cycle known to medieval astronomers was called precession. It's the cycle of precession, and I'm going to talk about medieval perspective on precession in a minute. But before I start, I think it might be useful if I bring us up to speed by briefly introducing our modern understanding of what precession really is. So let's take a gander at this sweet little animation. There it goes. So this is planet Earth, and Earth has a rotational axis, which is inclined by about 23.5 degrees relative to its orbital plane, also known as the plane of the ecliptic. Now, if we expand the equator into space, we get another plane, the equatorial plane. And these two planes intersect at 2 points, which are also known as the equinoctial points. Now, as you can see from the animation, these points actually move in space. They go in a circle. That's because the axis of the Earth, the rotational axis, doesn't stand still, but it changes its orientation over time. And that phenomenon is known as precession. It leads to a displacement between the equinoxes on the one side and the stars in the background. So the vernal point, for instance, will move through all the constellations that line the ecliptic. And as you know, there are 12 such constellations, the signs of the zodiac. And this entire cycle takes about 26,000 years to complete. So that, in a nutshell, is precession. Of course, this is our modern understanding, which is based on Newtonian gravity, so we understand that because of gravitational effects in the Sun-Earth-Moon system, the axis of the Earth is sent on this gyroscopic motion. But the phenomenon of precession, the very fact that the alignment between equinoxes and solstices on the one hand and fixed stars on the other changes, has been known for a long time, at least since the 2nd century BC. It was also known to medieval astronomers. And believe it or not, knowledge of precession was actually useful for telling time. And this is largely due to the existence of these things right here, astrolabes. Astrolabes are both analog computers and physical models of the cosmos. They use stereographic projection to produce a 2D model of celestial circles. And a standard part of every astrolabe is this perforated, rotatable disk known as the spider's web, or rete. And on a rete, you always have pointers representing the locations of particularly bright stars. It's a very nice specimen from early 14th century England, where the pointers are the beaks and tongues of birds and other strange creatures. And by rotating this disk, you're able to simulate the rising and setting of these stars. And that can be used to tell time during the night rather accurately, provided, of course, the stars are correctly positioned. And that position will change over time due to precession. So medieval astronomers needed to be able to update their astrolabes using these things right here, star tables, which give you the current coordinates of stars, longitudes, latitudes, declinations, and so on. There are essentially two ways of creating a star table. You can observe stellar positions, or you can take an older star table and just update it by adding a constant which represents the change in precession over time. It's that latter approach that was usually taken in the Middle Ages. And the interesting thing is that astronomers didn't always agree as to how to calculate this constant. There were basically two competing models. And it's precisely that conflict between these models that shall concern me for the rest of this presentation. In order to understand the nature of this conflict, we need to go back to basically the beginning. We need to go back to Ptolemy, greatest of all the Greek astronomers who lived in the 2nd century AD, and he's really the first astronomer that we know of to provide a proper theory of precession. He didn't discover the phenomenon, but he theorized upon it and gave us a coherent model. So according to Ptolemy, precession is the result of a slow revolution performed by the sphere of the fixed stars. He imagined all the stars to lie on the surface of a gigantic sphere, and that sphere revolves around the poles of the ecliptic, according to Ptolemy, at a rate of 1 degree per century. Another important insight on Ptolemy's part is that we have to differentiate between two different types of solar year. If we accept precession, we have to differentiate between a sidereal year, which is the sun's return to the same fixed star, which will be typically a bit longer than 365.25 days, which of course is the length of the Julian year. And the other alternative, or the other definition of the year, would be the tropical year, which is slightly less than 365.25 days. And the tropical year is, in Ptolemy's case, is the sun's return to the vernal point, or the vernal equinox. So the difference between these two definitions of the year accounts for precession. The larger the difference, the swifter precession progresses. Now, if you've paid attention, you will remember that precession takes 26,000 years to complete, But if Ptolemy is right, it should be 36,000 years, because it says it's 1 degree per century, and the ecliptic has 360 degrees. So there's a 10,000 year error here, which is not all that trivial, even by ancient standards. And of course, the question is, why did he mess this up so badly? And the answer is essentially hidden in his value for the tropical year. According to Ptolemy, the tropical year lasts 365.25 days minus 1/300. And that's about 6 minutes too long. And that's significant, because if you want to establish the rate of precession, you need to be able to compare stellar longitudes, tropical stellar longitudes measured over a long period of time. You can only get these longitudes if you have solar longitudes, and you only get solar longitudes if you have a measure of the length of the tropical year. One way of gauging the error in Ptolemy's solar theory is to look at a deviation curve. All you need to know is that this curve points downwards. That means the error increases over time, and his calculated solar longitudes lag behind the actual observable ones. And that's the reason why his rate of precession is too slow. Now, as far as ancient astronomy is concerned, that's about as good as it got, but things were improved drastically in the 9th century thanks to Arabic astronomers. For instance, Al-Battani. Al-Battani was active in the late 9th century in Syria, and this is his deviation curve. It goes the other way, which means that he slightly underestimated the length of the tropical year, and his precession rate, as a result, is a bit too swift. It's 1 degree every 66 years. Perfect would have been 1 degree every 72 years. But all the same, this is a considerable improvement. And for Arabic astronomers who came in Al-Battani's wake, the big question was, how do we account for this discrepancy between Ptolemy and Al-Battani? Should we just ignore Ptolemy and go with Al-Battani? That seems like an obvious answer to us. The problem is that the Almagest, Ptolemy's great work on mathematical astronomy, is a treasure trove of ancient data, including Ptolemy's own. And if you want to establish parameters such as the solar year or the rate of precession, you need to be able to compare observations made over a long period of time. And the Arabs really needed this ancient data to, get along in their own astronomical research. And since Ptolemy was a very important authority, just ignoring him or accusing him of error was not really an attractive option. So most of them went for another option, which was to say, hey, maybe the parameters changed between Ptolemy's time and Al-Battani's time. So the challenge is to find a model which accounts for this change. And by the end of the 11th century, that model had indeed been developed. It's known as the axis and recess of the 8th sphere. So it's a particular description of how the sphere of the fixed stars move, which implies changes in direction and also changes in speed. Axis and recess is just a straightforward translation of the Latin accessus et decessus, or accessio et decesio. You could also call it the back and forth, the towing and throwing. That's all very nice. Modern historians call it trepidation. It's an anachronistic term, but that's what we use. And it rolls right off the tongue, that's why I'm going to use it as well. I don't have much time to really explain in depth how this works, but all the same, let's just take a brief look at some modern drawings. So what you really need to know is that you have the 9th sphere, which is the sphere responsible for the diurnal revolution of the heavens. Inside the 9th sphere, there's the 8th sphere, the sphere of the fixed stars. And we just imagine that both of these spheres have an ecliptic projected on them. And on the sphere of the fixed stars, we have a mobile ecliptic, which is mobile because on that sphere you have 2 points. These are 180 degrees opposite of each other. We designate them as the heads of Aries and Libra. I think the one diagram really have to pay attention to is the one in the bottom right corner. So we have the heads of Aries and Libra, and these go on these small circles. And these circles are centered on the celestial equator, more specifically at the point where the celestial equator meets the mean or the fixed ecliptic of the 9th sphere. And by going on these small circles, the head of Aries always being 180 degrees removed from the head of Libra, you get a rocking back and forth and up and down motion, which has a number of different implications. The obliquity of the ecliptic will change, precession will sometimes reverse its direction, and precession never stays the same, it's always changing. And in fact, it changes in a sinusoidal manner. That gives you the rough idea. So that's basically the elongation between our hypothetical head of Aries and the vernal point. Whenever we are at the trough or cusp of this sine wave, we've reached maximum elongation in one or the other direction. It's plus or minus 10 degrees, 45 minutes. And at that point, precession comes to a standstill, and then it reverses direction, speeds up. And when we're at 0, that means the vernal point and the head of Aries are identical. And that's when precession has reached maximum speed and it slows down. Maximum is reached, maximum elongation is reached, and then precession reverses itself. It's a cycle that will last a little more than 4,000 years. But this is obviously completely bonkers. So the question is, why did they come up with this precise model? Well, the reason can be discerned by comparing the 3 deviation curves. That's the one by Ptolemy, you said earlier, that's Al-Battani. And that is the deviation curve for the mean tropical sun in the so-called Toledan tables. Because as we've known since 1996, this whole model was conceived in order to go together with a set of astronomical tables constructed in Toledo in the 1070s by Muslim Andalusian astronomers. And these tables, unlike those two, are based on the sidereal year. The sidereal year is the reference frame, the measure for calculating planetary longitudes. But you could still convert the sidereal longitudes into tropical ones if you converted them according to this model. And the resulting deviation curve looks like this. It's obviously nonlinear, but the way it's nonlinear is really quite remarkable. As you can see, it starts off looking like Ptolemy's, then it reverses direction, and then it goes the same way as Albertani's. And then you have a period of about 200 years when you get excellent results because it stays very close to the zero line of this deviation curve. And then the system takes this huge nosedive. That's the Toledo trepidation model in a nutshell. It's supposed to give you this curve. It's supposed to harmonize these two authorities and at the same time give you excellent predictions for the present between, let's say, the 10th and the 12th century. Now, this is all from Andalusia, but of course, this is being exported to Latin West in the 12th century. And as so often, transfer of knowledge goes together with transformation of knowledge, or new contexts are opened up. That's precisely what happens here. So Latin Christian scholars, when they look at this model, find applications for it that probably didn't even occur to their Arabic predecessors and colleagues. One very nice example can be found in this English work on time reckoning. This is from 1175, written by a fellow named Magister Conestavulus. We don't know a whole lot about him, but he was one of the first computists, one of the first experts in ecclesiastical time reckoning, who really made an effort to bring in all this new knowledge from translated Greek and Arabic sources. And one example for this would be his 36th chapter, which deals with the question why the solstices and equinoxes are no longer found on the dates on which the ancients found them, which is a question many computists in his time asked themselves, because they were faced with this problem. In their own traditions, in the writings they studied, they found two diverging conventions as to when the vernal equinox and by extension the other equinoxes and solstices happens. There's an old Latin tradition which puts the equinox on the 25th of March, or says it oscillates between the 25th and the 26th. There's a Greek tradition which puts them 4 days earlier, and the Greek one is very authoritative because Easter reckoning is based on this tradition. Easter can never fall before the 22nd of March because the vernal equinox is supposed to be on the 21st of March. And yet, in the 11th and 12th century, when computists made their own observations, and they did, they found the vernal equinox is actually much earlier, in the 16th or 17th of March. So how do we account for this? Well, Conestavulus goes one step further and takes the Almagest and other newly translated astronomical texts and mines them for ancient observational data. And he finds quite a bit of them. So he was able to create this little list which shows that between the 5th century BC and the 9th century AD, there was the shift of the vernal equinox from the 25th of March to the 17th of March. And that seems to speak a very clear language. The message seems to be that the Julian calendar, which the church used to place the equinox and solstices, was not correct. The Julian calendar overestimates the length of the tropical year, hence the shift in dates. That seems to be the obvious conclusion. So that's where Conestavulus steps in and says, no, wait a minute. Let's take a look at the Toledo trepidation model. So these, of course, are numbers generated by modern software, but he comes to a very similar conclusion. He points out in his own time, the length of the tropical year was supposed, ex hypothesis, according to this theory, was supposed to be getting longer and longer to the extent that by the year 1366, it has reached almost the precise length of the Julian calendar, by which time the vernal equinox has moved to the 13th of March. Beyond that year, the tropical year grows beyond the Julian year. As a result, the vernal equinox will move back in the calendar towards the later days. And this trend will continue until the year 3896, as you can see in the column to the right, by which time the vernal equinox has reached the 19th of April. After that, the tropical year drops below the Julian threshold again, and the vernal equinox goes the other way. And this will continue forever, essentially. These are the extreme dates, and he identifies them correctly. This is really quite impressive because it's not possible to deduce any of these data straightforwardly from the tables. The tables are not designed to give you that kind of information. You really have to calculate every equinox every year to come up with something like this. So this is really quite impressive on Conestavulus' part. And his message is clear. He's an apologist for his own calendar. He says, our calendar isn't wrong. No calendar is either right or wrong. They're all just snapshots of some moment in the past or the future when they are correct, and in between the length of the tropical year changes. And as you can imagine, this whole idea of a variable tropical year and of trepidation causing it played a very important role during those 400 years that led up to the Gregorian reform of the calendar. That was one of the major scientific problems they faced before they finally reformed the calendar in 1582. So it's one of those specifically Christian contexts for trepidation. The other is geographical in nature. This is essentially the view of world climate zones before the 12th century. These types of maps stem from the work of Macrobius. The idea is that you have two temperate zones, one in the northern hemisphere, one in the southern hemisphere, and they happen to be between the tropics and the Arctic and Antarctic circles. Beyond the Arctic and Antarctic circles, it's too cold for human habitation, and between the two tropical circles, it's just too hot. It's also known as the torrid zone. Don't go down there. That's the message you get in these texts. And that creates certain interesting theological conundrum, because obviously people live in the northern hemisphere. That's where Europe, Asia, and Africa are situated, also according to this map. And there should be a temperate zone down there, including some sort of fourth continent. But if nobody can move from the north to the south because of this hot, seething belt of torrid climate, the question is, if there are people down there, how can they be descended from Adam? How can they be subject to original sin? How can Jesus have died for them? How can the good news of the gospel reach them? That's the major reason why theologians throughout the early Middle Ages denied the existence of the so-called antipodes. The 12th century changes the variables a little bit, because we get a new view of climate. This is a map that goes back to the works of Petrus Alfonsi, so the origin is 12th century. Here the south on top. What this map tells you is that, contrary to this model, the equator is actually the most temperate zone, with the best, the most beneficial climate. But as soon as you go beyond the equator, the southern hemisphere, that's desert. That's uninhabitable. That's what this map says. The entire southern hemisphere is uninhabitable. The reason that this idea took hold in the 12th century as a result of knowledge transfer has to do with the Ptolemaic solar model, which we talked about earlier today in our symposium. So we have this eccentric model of the sun going around the Earth. You have an apogee and a perigee. And it just so happens that the perigee is in the southern side. It's very close to the Tropic of Capricorn. It's in Sagittarius. The apogee is in Gemini. And of course, this eccentricity is much exaggerated. So it became very plausible to think that the sun comes so close to the Earth when it's at perigee that it really burns the lands below. And these lands happen to be in the southern hemisphere. So in a way you can say, hey, we disprove the existence of antipodes scientifically. Isn't that neat? But there is one problem here. And that's precession, because as the Arabs found out in the 9th century, the line of apsage which connects the apogee and the perigee, they partake in precession, or at least they have a motion which they assumed partook in precession. And that means eventually the perigee will be in the northern hemisphere. It will burn the lands of Christendom, and we will all have to migrate to the southern hemisphere if we want to survive. And that's not a very encouraging prospect, and that's one reason why trepidation was often appealed to. Because according to trepidation, the perigee can never leave the southern hemisphere. It will only go 10 degrees 45 minutes in one direction, 10 degrees 45 minutes in the other direction, and we are safe. And that's basically the conclusion you find in plenty of 13th century texts that Acessus et Recessus is a guarantee against major global climate change. Yeah. And Robert Grosseteste is probably the first to make that point, at least allude to it, but he has plenty of followers in that regard, and that certainly contributed to the attractiveness of that theory. Now, if you read literature on the history of astronomy in the Middle Ages, you get the idea that trepidation was really the only game in town until Copernicus, and it's only later on with Tycho Brahe that serious criticism is leveled against that theory and that they exposed it as a result of observational errors committed by Ptolemy. But that's not really the case for a number of reasons. For one thing, there is opposition to trepidation in the 13th century. As far as I know, it starts in 1246 with a letter written by John of London to a friend of his, where it just starts off basically by saying, you know what, I found out trepidation is just nonsense. And there are various reasons why these authors had doubts about trepidation. A major reason can be discerned by going back to this deviation curve. It's another close-up of that deviation curve produced by the Toledan tables. You have this nosedive here. So there's a drastic deterioration of predictive accuracy. And that becomes really noticeable around 1300, where you have discrepancies of a degree or more. And it's no accident that as soon as you get to the 1290s, you find observational records by Latin astronomers, like this one by Pierre of Limoges, who was active in Paris in the 1290s, and he left an entire page of observational notes, observations he carried out with a friend of his, Franco of Poland. And these two men found, for instance, the vernal equinox in AD 1290, then on the 12th of March, 4 p.m. And they used that to establish the elongation between the head of Aries and the vernal point, and it turns out it exceeded the Toledan prediction by 50 minutes. That's a significant error. And that is really part and parcel of that movement of emancipation when astronomers grow dissatisfied. And one type of source that really shows you this without making the point explicit are star tables. So if you analyze star tables, you will find examples of star tables which were obviously calculated by adding a constant to Ptolemy's longitudes, for instance, but the constants don't match the Turian model. They were obviously calculated using linear estimates for trepidation. So for instance, on the left, we have a star table from 1314 that's basically calculated using Albertani's model. On the right, we have one from England from around the same time. That uses an even more accurate estimate, 1 degree every 70 years. That's also an estimate that comes to Latin West from Arabic and Hebrew sources. And there are other examples like this. And there are even cases of Latin astronomers trying to figure out their own rate of precession. For instance, this astronomer from Bologna, who was active in 1306. So he compares his own observation of Spica, Alpha Virginis, with the longitude observed by Ptolemy and comes up with, hey, it must be 1 degree 72 years, which is of course exactly right. So that's about as accurate as the Middle Ages got in that department. And that's basically the point I'm trying to make. You really have to go back to the manuscripts, examine star tables, examine observational notes to see how rich the discussion was around that time, and precisely when there was a crisis, because the existing model no longer yielded accurate predictions, and that's what I'm working on at the moment, and that's why I'm talking about this, obviously. And now I'm very grateful for your patience because I've come to my end. Thank you very much.
So, how's this going to all fit in? Well, I guess I'll give the talk and we'll see how it works. There's an interesting addendum to what we were saying, but we'll come back and see if anyone in the audience spots that in a minute. So, what I wanted to... giving this talk made me think about what do we mean by time in current cosmology, because we kind of tend to be working at the coalface, we're busy working on computer code, improving it. Nobody really thinks about what do we mean by time in modern cosmology. So it was very useful to take a little step back and think about how our notions of time have changed. And what I'm going to base my talk on is a lot of numerical simulation work. So I'm going to show you some movies because it's getting late in the day and somebody once told me if you're giving the last talk of a meeting you better have a good movie. So boy, have I got a good movie for you. And what we do is we try to simulate the creation of the cosmos. Now the great thing that we're able to do now is we understand, or we think we understand, the laws of physics. So if we apply those laws of physics, we can program up the computer, we can press go on the computer, and we can see how the universe should develop. And we've recently been making a lot of progress in trying not to just create the kind of big structures of the universe that you see here, so this kind of cosmic web of structures, but also to go and create individual galaxies within the universe, so the individual collections in which you find stars. And so this is a large-scale view of our little piece of universe that we've made. It's about 50 megaparsecs here, so that takes light to cross this box, about 150 million years. And I'm going to zoom in on a little patch here. And if I blow up this little patch, there's enough information in the computer that I can then blow up another tiny little patch. And if the screen was slightly better, you could see this is actually a galaxy, like our Milky Way that's formed there. So I love going to astronomical societies and showing them this picture. And I usually show them picture and they go, oh yes, last night we took a photograph of this one, and oh yes, last time we were photographing that one. Then I point out that these are all galaxies found inside the universe that we've created inside the computer. It's just really astounding that we can get to this kind of level of reality by programming the computer with the laws of physics. Now, I think at this point, what I need to do is talk a little bit about the history of the universe, because I was trying to guess how much people in the audience would know, but let me bear with me if you already know this, and slow me down if I'm going way too fast. So, how do we do this? What are the stages that really happen in our modern universe? Well, the universe starts with what's called the Big Bang, but now we kind of have an idea of what we don't know about the universe. So you can go and you can try to compute when do the laws of physics break down. And if you go back in time to when the universe was earlier and earlier and earlier, because of the expansion of the universe at very early times was very hot and dense. And you have two important theories that play a big role in shaping the universe we're in. You have gravity, which we can do with Einstein's general relativity, and you have quantum mechanics. And one of the great predictions of Einstein's relativity is the existence of black holes, things that are so dense that nothing can escape them, not even light rays. And at the same time, you've got the great theories of quantum mechanics, and that tells you if you look on really small scales, you can't know both the position and the velocity of something. So if I try to zoom in and look at something really great detail, eventually I won't be able to do that. And so we know when things go wrong, when I have a black hole that's so small that I don't know where it is, essentially. And you can actually go and calculate that, and it comes up with something called the Planck Scale, and you know that the only way to understand that would be to have a consistent theory of both quantum mechanics and general relativity. And that doesn't exist in a way that we understand what it means. People have proposed such a theory, but then trying to extract anything from the mathematics proves impossibly difficult. So we don't know how the universe begins, but a good idea is that at the beginning of time there was no time because of this uncertainty in everything, that there was basically just a foam of stuff. It has a lot of resonance with what Neil was talking about, the infinity of God. Oh, I better not go there, that's dangerous. But, so there is no time, it just exists. And then out of this space-time foam, a little piece manages to last long enough that it begins to grow because of its unusual high energy. And the growth of that little point allows it to blow up like a balloon. And that's kind of how we understand the beginning of the universe. Now, it's a story. How do we know what it looks like for real? Well, fortunately, the theory of this we can write down. It pushes our knowledge of the equations, but we can predict how the universe would expand. And one of the predictions is that the universe would not be completely uniform, would be full of little tiny irregularities in it, okay, arising from the fact that this was a quantum process in the first place, so it's not got a certain single value. Now, luckily, trying to compute those would be impossible, but luckily we can now observe these. They leave an imprint on a very distant universe. And so when I say we're going to compute the history of the universe, I can't start at the very beginning, but I can take these small, tiny irregularities and see how they would grow over time. Okay. And the idea is the universe then, because of this high initial period of inflation, and continues to coast outwards. It gets larger and larger, and as the universe expands, that's also equivalent to cooling it down. Okay? Just as if you feel the air coming out of an air pump or something like that, the air is actually very cool as it's expanding. And the same process is happening in the universe. It's getting very cooler and cooler, and that turns the initial raw energy of the universe into the actual particles. Okay. So this process of the expansion of the universe is then very important, and what's going to happen is the gravity is then going to be able to collect these particles of matter together to form structures. So I can now start from these initial small fluctuations, turn on the calculation of gravity. I know how to do that well, and let the computer do its job. And so this is a little part of a calculation showing this, and you can see how you build up this web-like structure of the universe, okay, over time. Now, this makes a nice picture, but it's kind of a little bit deceptive, because what we always do, and what we tend to forget in modern astronomy, is this is really expanding as well. So I've taken a little cube, but that cube is actually growing over time and getting bigger and bigger. And I've also done tricks to make it look like things happen at a uniform rate. They don't happen at a uniform rate in terms of if I sat and had my watch and watched the structures of the universe going past, they wouldn't form at a uniform rate like they do in this movie. So, that kind of means that in astronomy, in cosmology, we're reinventing what we mean by time, and I think we don't normally acknowledge that, right? It happens just because computer code gets written in a certain way. But in practice, what's going on is we might normally think of time as being a measure of, or astronomical time at least, be a measure of how long it takes things to go round and come back to where they were in the first place. Our common notion of time, so for instance, we know how long a day is because the Earth goes around, we know how long a year is. Okay. But what happens in cosmology is because the universe is expanding, everything is getting less dense over time, and so I can simulate that using Keynote. Right, I think that was a bit challenging for PowerPoint, but here you go. So this is a simulation of the expansion of the universe, and basically all the time scales now take an awful lot longer. So the universe kind of, as it expands, slows down, and things take longer and longer to happen. So cosmic time scales are not constant. So our ideas about time, implicitly in cosmology, we tend to think about things in terms of this time scale, which is related to the density of the universe. So it actually means as the universe expands, the density here in this formula is going down, so the time scale on which everything is happening is longer and longer, and the universe slows down. Okay. So this introduces the notion then that rather than thinking about time in the usual way measured on my clock, I can maybe think about time as being the expansion of the universe and how the universe has grown over time. And we often measure this then, what in computer codes becomes important is the expansion factor of the universe. How big is the universe relative to its initial size? Okay. Now, luckily, it's possible, one of those miracles of the way the universe is set up, that as the universe expands, light gets stretched. So if I look at a distant object, I can see, in this case, an emission line due to the molecule of hydrogen. And I know from looking at lots of spectra like this, that this line is really the Lyman alpha transition of hydrogen, which should have a wavelength of about 1260 angstroms. And I look at this observed spectrum, and I'm seeing this transition is now occurring at a wavelength of almost 5,000 angstroms. So what's happening? Well, it's the expansion of the universe has expanded the wavelengths of these oscillations, and so I know, I can call it, this is what's called the redshift, I know how big the universe was when that light was emitted compared to now. So it's really quite remarkably convenient that I can kind of now, by observing this distant object, actually look back in the past and see what things were like when the universe was much smaller. and I've got access to that information directly. Of course, I need a big telescope to do this because I'm ever wanting to look further and further into the beginning of time, which means that the telescope has to get larger and larger to be able to make measurements like this. Now, the other thing whilst I was putting this talk together that occurred to me is, what happened to all the questions about general relativity, causality, all those kind of nitty-gritty questions raised by Einstein's special relativity? Turns out they're weirdly irrelevant, because once you take into account the expansion of the universe and rewrite the equations in that reference frame, everything actually looks like it was written by Newton. Okay, there's just a little subtlety to how you interpret some of the numbers in the equations. So we don't have any of these causality issues with time, which is kind of weird, you'd have thought, with the cosmos. Okay, so that was a little bit thinking about time, and if you put this in the computer, you end up with movies like this, forming a nice object at the center of this little patch here. This is actually quite a zoomed-in view compared to everything you've seen so far. And we know that the universe now is mostly filled with matter that you can't actually see. So somebody came up with a clever term of dark matter for this mass. Focus Ringel has invented this color for dark matter. So I think when it's discovered, we're going to discover it's this kind of pinky yellow color. And the colors kind of illustrate the density of dark matter in the universe. And so if you had dark matter glasses that you could put on and look at the universe, it would look like this. We would have a good description and a good notion of time in the universe. Okay. Unfortunately, what we really want is to understand where the stars and galaxies are in this picture. And you can kind of guess, oh, well, I bet there's a big galaxy here. But the challenge is now to understand how did the galaxy actually get there at the center of this. And the interesting thing that's emerging from the work we do is this kind of competition that the way gas gets to the, or material gets to the center is kind of like this cartoon that I think I did in my PhD thesis, and it's amazing that it's still even vaguely relevant today. But that gravity assembles matter, but the matter it assembles is hot and diffuse, and stars are made up of basically fusion reactors that are incredibly hot, incredibly dense, so that the gravity can stop them blowing themselves apart. And so how does the gas get so dense? Well, the reason it gets dense is by emitting photons. Okay? And that cools down the gas. As it cools down, it then collapses into a spinning disk. And this is basically the story of galaxy formation. But the interesting thing is that there's a whole different time scale going on here. We have the expanding universe time scale that was collecting the matter together and bringing it into one place. But there's this competition, there's a different time scale. And this is related to quantum mechanics, and hence my claim, there's an atomic clock at work in the universe, determining how we go from the collected matter to the formation of the galaxy itself. Okay, so the universe's complexity arises from the interaction of these two things. So, for instance, this is a plot. Am I allowed to show plots in this? Well, I've done it, so it's too late. But this is the star formation rate of the universe, the rate at which the universe forms stars. It's a logarithmic plot, so the difference between the rate of formation of stars at the maximum of the universe and today is about a factor of 10. So the universe was a much more active place in the past, about 8 or 10 billion years ago.
So which is the present is the origin here.
So sorry, yes, thank you. So the present is over here, okay, and the beginning of the universe is over here, but a little bit further than this axis goes. Okay. And the observations are shown as these data points with error bars. Okay. And The simulation results are amazingly this black line, and there's a correction you need to add because we only can calculate a small part of the universe, and our estimate of that correction gets us to this grey line. So it's really quite incredible that we do so well at reproducing this plot. But the interesting thing about in terms of the nature of time is that there's a rise here in the rate at which the universe forms stars, and this is due to that atomic clock holding things up. The structures are being formed very fast, but stars form relatively slowly, and that kind of slows down the creation of stars. But then later in the universe, the accumulation of structure is declining, and so this is causing a decline in the rate of star formation.